Okay, hello everybody. I hope everybody out there is doing really well. Hello to some of the regulars who've already joined the chat, which is amazing. So basically, tonight we're going to be doing some more questions about physics. So yeah, that's all good. So I'm just checking some stuff here. So basically, oh my gosh, there's so many people here. Matty, Katsuri, Joe, Suspected End, Nathan, like Yvonne, Ethan, great to see so many new people in the chat. So it's probably, only a few weeks away till GCSE, so we're going to start with some GCSE content, and this one here is to do with electricity and paper 1, so these are the questions we're going through. If you want to find and download your own copy, I've put a link in the chat, and obviously there's a link underneath this video to my physics online shop. You can buy a digital set of papers, you can buy just the one paper, or you can buy the whole set of 12 papers, and I guarantee that if you do all of these kind of practice papers I've put together, in addition to obviously all the work you've been doing in class, the other kind of past papers and things like that, I guarantee that you will get a higher grade and you'll get more marks in your exam. Okay, so PTR says, hello first of all, you sat your A-levels 3 years ago and you just sat your quantum mechanics exam yesterday. So PTR, I'm sure that this will be pretty straightforward compared to what you've just been doing. So yeah, hope that all went really well, and it's great to have so many people who've kind of used the channel beforehand and have continued on to great things. Somebody else says, do I make chemistry and biology papers? No, I am purely physics. I'd rather specialise in one thing and do it really, really well than try and do a bit of everything. So all I've got is the physics content, but of course that's all you need to kind of really boost the rest of your marks. That's really the most important one, in my opinion. Okay, so somebody has their exam on the 13th of May. Any suggestions? Yeah, I would say that the 13th of May is still like 10, 11 days away, and there is a huge amount of time to really consolidate your knowledge, work on the kind of things that you find most difficult, and you can make massive improvements in that time. And also, by the 13th of May, you will have been doing some exams already. You'll have got over your initial exam nerves. You know where to go for the exam. You know the format. You know the system. And that means, because you're happy with the way that exams are running, you can just concentrate on the content. So, something that I think a lot of students do struggle with or find quite difficult is this subject here, looking at electrical circuits. Now, my suggestion is that when you get a question like this, add bits to the diagram, and this will make everything a little bit easier. So we've got an electrical circuit, we've got the fact that it's made to look at some of the rules around direct current circuits. So it says the current through the 4 ohm resistor is 2 amps. So I'm just going to put, I'm actually going to do it in colour for this. I'm going to put that the current here is 2.0 amps. And the potential difference across it is 8 volts. So I'm going to use a green to say that across this, the potential difference is 8.0 volts. Okay, and I'm just going to put that like that to show that this is the potential difference across that component. State the current flowing through the 2 ohm resistor. So what is the current that's going to be in this resistor? So it's 2 amps here. We've got 2 amps in the 4 ohm resistor. What is the current through this? And by the way, some people have already got the right things. Abdullah, yes, straight in with the correct answer. And this one over here, there's no calculation needed. What we have is a question where you need to state the answer. Now, if it says state, that means the answer's already been given to you somewhere and you don't need to do any calculations. So Matty, Feather, Chop, Suspected End, Abdullah, 2.0. Yeah, so the current is going to be 2.0 amps at that point, because in a series circuit we have the same current everywhere. So no matter where you put an ammeter, we will always have 2.0 at every single point in that circuit. Okay, so we don't use up the current as it goes into a component. Instead, we have the same current flowing everywhere. And yeah, the slow-mo says, yeah, is that because the current is the same in all series circuits? That's right. Okay, describe how the current through the 2 ohm resistor should be measured. So this one over here, again, a lot of questions at GCSE, they're not actually that difficult. And in answer to GG, 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 do I have any specific topic predictions for this year's paper? I would say my prediction is there's going to be a question about putting an ammeter in series or a voltmeter in parallel. We'll see how correct I am when the actual exam happens. So, describe how the current should be measured, and it's at this point over here. What you need to do is you need to use an ammeter in series. Okay, and that gets you the marks. First of all, we've talked about the measuring device, the ammeter, because we're looking at current measured in amps, and it has to be in series. So you'd put it effectively either here or you'd put it over there. And it doesn't really matter, to be honest, actually, where you put the ammeter. You could put it here, 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 anywhere in that circuit you could put the ammeter, and it will always read 2.0. The slow-mo says you could use a multimeter in series, and I would say that if you're talking about using a multimeter, you need to say that you've used a multimeter set to the ammeter settings. Okay, so you make it really, really clear. Yeah, does it just mean next to it, Matty? Yeah, that's all we mean. So basically, you basically have one thing after the other in a single loop in a series circuit. Okay, right. Calculate the potential difference across the 2.0 ohm resistor. So what we're going to do now is imagine we had a voltmeter in parallel with this, and therefore we want to measure the potential difference. What would be that value there? Well, we have a supply of 12 volts, and there's going to be 8 volts across this, so what's left? Because what we have in a series circuit is we share or we split up that potential difference. So a lot of people, again, getting the right answer. Abdullah, a suspected end, great stuff already. You could either subtract from 4 or use V equals IR. So yeah, basically, there's two ways of doing it. The first way is we could say that in that circuit, we've got a 12 volt supply and 8.0 volts is across that resistor. And so you take 12, take the 8 away from it, and that's equal to 4.0. So the answer is 4.0. So that's the first way of doing it, just by looking at how we share out or split apart that potential difference in that circuit. Abdullah also says you can use V equals IR. So let's use this. We can say that V equals IR. Now, the potential difference is going to be the current in that component, which we know is 2.0 amps. And we know the resistance of that component is 2.0 ohms. So 2.0 times 2.0 is, of course, also equal to 4.0. So I think what we find with a lot of questions about circuits is that there's more than one way to actually have a go at that. There's more than one way to get the correct answer. In real life, would the voltage really equal 4, says Slow-Mo? In an ideal circuit, yes. In reality, what you might have also is there's going to be some resistance in the wires. For those of you doing A-level physics, you know that we often have internal resistance inside the cell or the battery. And in reality, if that was 12 and that was 8, this might be a reading of maybe 3.9, because there'd also be a potential difference across the resistances of the wires. But of course, this is our perfect GCSE circuit where everything works really well. Okay, hopefully that's all good. So at the moment, if you're understanding this, which everybody seems to be in the chat, you're doing super, super well. The next question, describe how the potential difference across the 2.0 ohm resistor should be measured directly. So rather than calculating it, how would we actually measure it? So what we need to do is actually very similar to the answer that we had. And go global, Layla. I'm going to answer your question. In a resistance-free wire, would there be no potential difference across the wire? Yes, that's correct. Because if we think about V equals IR, if you had, if you wanted to work out the potential difference, imagine the current in that wire was 2.0 amps, but the resistance R is 0. Then the potential difference across this would be equal to 2 times 0, which equals 0. So in an ideal circuit, and in GCSE, and actually most of the time at A-level, we assume that all of the wires have 0 resistance. Okay, the slow-mo, Matty, Dayton, yeah, great to have people there. A suspected end, Ethan, excellent stuff. So for this one, you just need to say, with a voltmeter in parallel across the 2.0 ohm resistor. Okay, so what we have here is we need to talk about the measuring instrument, the voltmeter. We need to say it's in parallel, but also we need to say it's only across the 2 ohm resistor, not across that whole part of the circuit. And Matty, the reason is that ammeters basically measure the current going through something, and the voltmeter measures the potential difference across each side of that component. It's just the way it is. Okay, so excellent stuff. Again, it's great to have so many people in the chat, and it's really nice to have the same people coming back night after night. Mustang, which paper is this? That's a great question. So this is one of my own practice papers that I've produced, and if you want to buy a copy, you get the paper, you get a mark scheme, you get a set of work solutions, and if you've got a premium plan or a school subscription, which I would say, if you haven't already got one, go and buy one on my website, which is GCSE Physics Online. That gives you access to hundreds more videos, and also there's a video where I explain all the answers to the entire paper. I can't remember which paper this is tonight, but what you can do is check at gcsephysicsonline.com/live, and I think it's either a beta or a gamma. Okay, state 2 different ways of calculating the equivalent resistance of the 2 resistors connected in series using the information given in figure 1. So what we have here is we've got a 4 ohm resistor and a 2 ohm resistor, but what is their equivalent resistance because these things are connected in series? So, so the first way you could do it is you could basically say that the total resistance or the equivalent resistance is equal to R1 plus R2. So effectively what we're saying is that this is maybe R1, this one is R2, and basically you could work this out by saying, well, R1 is 4 ohms, R2 is 2 ohms, and that gives a total resistance of 6 ohms. So the first way to look at the combination of resistances of resistors in series is to add them together. Okay, right, the next one is you could say that V is equal to I times R. Okay, and this is another way of doing it. And that means R, or the total resistance, is equal to the potential difference of that cell or battery divided by the current. Now it says here that's a 12 volt supply, so that's 12 volts. We know that there's 2 amps flowing in the circuit, and 12 divided by 2 is equal to 6.0 ohms. And what we have here is kind of a numerical way to show that. So basically there are 2 ways, but we need to kind of state this or describe it. And actually what I did in my set of work solutions, again you can download when you buy the paper. And this one here, CHOP ATR, it's a Gamma 1 paper. Yeah, so we've kind of done some questions from alpha. We're now doing questions from beta. Sorry, we did questions from beta. We're now doing gamma. And then over the next few weeks, as we prepare, or as you really prepare for paper 1, we're going to be doing some questions from delta, epsilon, and zeta. So these are basically the first 6 letters of the Greek alphabet. Now you're probably familiar with alpha, beta, and gamma in terms of radiation. That's just the first 3 letters of the Greek alphabet. And then we also have delta, we have epsilon, and there's like a zeta, which is a weird symbol like that. Okay, yeah. And I thought this would just mean that we're not getting confused between like paper 1, 2, and 3 or whatever, and we're not thinking about papers A, B, and C. I just thought if we call it Greek names, first of all, it's a good bit of physicsy kind of nerdiness, and also it just shows that there are 6 different versions of paper 1 that I've produced, and 6 different versions of paper 2. The slow-mo, well, I do behind the scenes while I make the papers. To be honest, me making these papers has been the most painful process of having other teachers, and I've worked with people who work for AQA, I've worked with lots of heads of physics to kind of come up with some questions. It's been Joe and Rufus editing stuff and me checking and then editing and then checking and then realising I've made a mistake, and it's like the most painful process. I reckon to do these papers, it's taken me a good 6 months of this year to do these papers. So by the way, if you do like what I'm doing, you can support me by buying papers, and that will support you as well. We're kind of helping each other. Okay. But on the work solution, I said you can divide the potential difference across the cell by the current through it, which is V equals IR, or you can add the resistance of the individual resistances. Right, state how the following quantities would be different if the two resistors were connected in parallel rather than series. Now for a question like this, all of you, even though it doesn't say to, draw a diagram. So originally we had the two resistors in series like that. Okay, now however we've got the two resistors in parallel. Okay, and that one's like 4, that's 2, that's 4, and that's 2. Now, if we also put this into that circuit that we had earlier, and we know that's a 12 volt supply, what's going to happen if we have these two resistors in parallel? What's going to happen to the potential difference across the 4 ohm resistor? Now before, we had two resistors in series, and they had 8 volts across that one and 4 volts across that made the 12. So we kind of split up that potential difference. However, now, what's going to happen to the PD across the 4 ohm resistor? We can say that this would increase to 12 volts. Okay, and both of these would have the same PD across it. So we'd have 12 volts across the 4 ohm and 12 volts across the 2 ohm. Because what we have, and this question really is about what happens to potential difference in current in a parallel circuit. Each loop in this circuit now has the same potential difference. Okay, what happens to the current through the cell? Well, basically now we have, for the same value of V, we now have a lower value of R, and this means the current is going to increase because the combined resistance, the total resistance of these two things is going to be lower because there are more paths for the electrons to flow through that circuit. So with a lower overall resistance, but the same value of V, this is going to increase our value of current. So the current would increase. Oh, increase. Okay, and that means we've got maybe the current going through this one, which would be I is V over R. So you don't have to, okay, we could actually calculate this. So the current through this loop is going to be equal to V over R, which is 12 over 4, which equals 6.0 amps. And the current in this part of the circuit, again, is going to be equal to V over R, which is now 12 over 4 is equal to 3.0 amps. And then 12 over 2 is equal to 6.0 amps. So actually, if we were to look at the current here, we'd have 9.0 amps, we'd have 9.0 amps over here, and that means we'd have a current of 9.0 amps actually going through that. So yeah, it is 3, isn't it? Do you need to know the reciprocal equation in GCSE? You don't need to know it. Now, for AQA, you need to know that when you have resistors in parallel, the overall resistance decreases. It's only for a couple of exam boards where we can say that 1 over RT equals 1 over R1 plus 1 over R2. Okay, now this thing here, you don't need to know this equation for AQA, but I think for WJEC you do. And yeah, right, Mustang, I should do a live on an IAL Edexcel paper. I will be doing a lot more questions for A-level physics, but I'm going to try and make them suitable for everybody. But I think I can't really use Edexcel papers due to copyright issues, so I can't show that on YouTube, I'm afraid. Arnie says, is this the Arnie? Best of luck for everyone in their exams, you'll be fine. Yeah, that's true. Yeah, awesome support there. Right. Okay, so Rahik says, in Pakistan they had a CIE maths paper leaked the night before. Right, I reckon that a lot of the time, and this is kind of like a serious but boring exam thing, okay? First of all, if a paper is leaked before the exam and the exam board know about it, they have a spare paper in reserve that they can send out. So first of all, if a paper is leaked and they know about it, it's really widespread, they won't use that exam in the real thing. Secondly, if there is a leaked paper, don't look at it beforehand, because if you look at the leaked paper, there's potential that you could then be done for cheating. And thirdly, if people offer to sell you a leaked paper, it might not be a leaked paper, it's just a scam. They'll take your money if you pay for it, and then they'll disappear. So a lot of the time, these kind of leaked papers that people are trying to sell occasionally, and especially on things like TikTok, I've sort of seen all sorts of bits and pieces. Mainly they are scams because they just want to get some money from some people, knowing that people are quite desperate. Okay, right. Okay, so that question there, not too bad actually. Right, the next one is about smoke alarms. Now, you do not need to know the full way that a smoke alarm works. I mean, if you go to my site again, I've got a video where I explain it. But basically, we've got a smoke detector. It uses a source of alpha radiation, and it might be useful when you read this to kind of think, okay, alpha radiation, that's going to be 2 protons and 2 neutrons, and it's therefore got a charge of +2. So this is our highly ionizing radiation. We've got 2 electrical terminals with an air gap, and it says as long as smoke is not present in the air gap, a small current flows between the 2 electrical terminals. So this circuit here, we've got a source of potential difference, we've got a battery over here, we've got an ammeter which is going to measure the current, and basically this plate is negative and this one is positive. And if you've got an air gap, there's going to be some kind of flow of electricity through it. So the first question is simple. You do not need to know any of that. All of you can state what an alpha particle is. Milkshake says a helium nuclei, perfect. Positive particle, 2 protons and 2 neutrons, suspected end. Slow-mo, HE. Yeah, I reckon a helium nuclei. And this is such a boring thing that only the kind of examiners are going to care. You could say a helium nucleus. So not a helium atom, it's the thing with no electrons on it, it's just the helium nucleus. Or you could say it's 2 protons plus 2 neutrons. Okay, so that is stating what it is. So you need to know that we've got 2 protons and 2 neutrons in the alpha particle. I reckon this question might come up this year in the exam about what is an alpha particle. So that is my top tip. Know this, it might well come up. So yeah, a helium particle would infer there's 2 electrons, which isn't quite correct, but it's the fact that it's a helium nucleus. Air is normally an insulating material. State the property of alpha radiation that causes the air in the smoke detector to become slightly ionizing. So what happens is, and this is kind of like the mechanism of what's going on, we've got an alpha source here. Now that source is going to be emitting alpha particles, and as the alpha particles basically move through the air, they're highly ionizing, and they're going to smash into the air particles, and they're going to knock electrons off. And this means we then have positive ions or negative ions. And what this means is that the air in this gap here has become ionized. So we have ionized air, and if it's an ion, it's got a charge, either positive or negative, and that means that like some of the positive ions are going to be attracted to the negative plate, the negative ones are attracted to the positive plate, and that means we now have the movement of charged particles, which is the definition of an electric current, and that allows an electric current to move around the circuit and be detected by the ammeter. So the property of alpha radiation is that, as people have said, it is highly ionizing. And I think I've seen a lot of people in the chat saying that this is the thing. So yeah, I reckon people like free maths lessons, it is highly ionizing. Perfect. Highly ionizing from Zeno. Yeah, excellent work there. So just be really, really clear. The slow-mo as well. Okay, right. Okay, state 2 reasons why gamma radiation would be unsuitable for this application. So we've got to have 2 reasons. We've got some good stuff here. So again, this question is about, do you know the properties of alpha, beta and gamma? So firstly, we could say it is only weakly ionizing. So yeah, so Nathan, it's so good to see so many people coming into the chat I've not seen before. Evil says low ionizing power, perfect. So Anissa says about it penetrating, and I think that's important. It doesn't stop in air, says Dian Patel. Okay, so firstly, it's only weakly ionizing, which means it probably won't ionize the air. And it has a long range, so could irradiate people nearby. Okay, so two things. First of all, it's only weakly ionizing. So if you had a gamma source here, it's not going to ionize many of these particles, and that means we get a very low current, so it's very hard to detect. The second one is that the other thing is that these things, the gamma, it's not stopped by a few centimeters of air like alpha, and that means you'd have a radioactive source which could kind of start to irradiate people nearby. And if this smoke detector is in a house on the ceiling, you don't want to feel any effects of that radiation. You don't want to be irradiated by having a safety device in your house. And so that means the alpha, it's only got a range of a couple of centimeters, and unless you're like 7 or 8 foot tall, you're not going to have your head next to this. Instead, if you had gamma instead, then that means the gamma would irradiate people nearby. Okay, so yeah, some great answers there. The next question is about thickness monitoring. So I'm sure if you're doing GCSE, you'll have heard about this. Basically, imagine you've got some kind of rollers which are flattening a piece of metal. So if anybody's seen like How It's Made, or the kind of thing on Discovery sometimes, great series, you often have like a factory making things. So you'll have some rollers which are kind of basically rolling a thick piece of metal to make it thinner. Now for this, we've got foil, and if it's foil, then it's made out of metal. Okay, over here we have a beta source. This is emitting beta radiation, and some of that is going to be going through to the detector. But of course, if you have a thicker piece of metal, it's going to stop more radiation getting through, and that means the detector will notice that change, and it can then be connected to the rollers to move them backwards and forwards to either make the metal thinner or thicker. So what could be used to detect the radiation? Let's see what people have said. We've got a Geiger-Müller. Slow-mo says a GM tube. Matty says a Geiger-Müller tube counter could detect it. Geiger-Müller tube. Joe, you've even put the umlauts in. I'm super impressed. Diane, Geiger-Müller counter. Anissa, GM tube, Geiger-Müller. Nathan, Chop, ATR. Evil, yeah, so suspected end. What we have is basically, you can call it many things. You can call it a GM tube, and the person marking this should be a physics teacher, so they know exactly what you mean. If you want to write Geiger-Müller, and I only kind of really learnt this recently, it's M-U-L-L-E-R, but there's 2 dots above the U. So if you just put Müller without the umlaut, is that the right word? I apologise if there are any kind of like German speakers in. There's like basically a double dot above the U, and it's basically a Geiger-Müller tube. But even if you don't have that, they know what you mean. Geiger-Müller counter, milkshake, perfect. Okay, what's the name of that symbol? I think it's an umlaut, isn't it? Yeah, okay, umlaut is correct. Thank you, Joe. Appreciate that. Right. Why would alpha be unsuitable for this application? Now, if you had alpha and you fired it towards this thin sheet of foil, what's going to happen is that all the alpha is going to be absorbed by this and it can't penetrate it. So the slow-mo says it would all be absorbed by the metal. And that would mean that it couldn't be detected. So if you had an alpha source here, this wouldn't detect anything, so it wouldn't be able to control the rollers. Whereas beta can actually penetrate that kind of thin sheet of metal and can be detected. Okay, right, and the last bit, we've got about a minute left. A manufacturer of medical equipment needs to sterilise the scalpel once it has been sealed inside airtight packaging. So again, diagrams help. Here is my plastic bit of packaging, and here is my scalpel. Okay, that's actually quite a hard thing to draw. Okay, so here's my scalpel. We've sealed it inside this plastic packaging. Why would alpha or beta not be the most suitable to sterilise the equipment? I reckon that both alpha and beta would be partially absorbed by the plastic, but gamma wouldn't. Okay, you can say stopped, Zeno. Yeah, that's perfect. Diane Patel, yes, at the moment, almost every night. I'm doing it 5 days a week, but I'm having a rest. I'm not doing it tomorrow night because nobody's going to watch on a Friday. Saturday night, you should be doing other things. And actually Sunday night, because it's a bank holiday on Monday, I won't be doing a session on Sunday night, but I will be back next Monday, Tuesday, Wednesday and Thursday, and then I'll be back the week after, I think on like the Monday, the Wednesday, the Thursday. Basically, if you want to find out what I'm doing in terms of these live streams, just head over to GCSEphysicsonline.com. You'll see a little live icon, click on that and you can see the plan for everything. And basically now, what we're going to be doing is just paper one focus stuff. So stuff like this every night, looking at questions, looking at common questions. And actually, I think even in the chat for people watching this live, I think it's quite useful because a lot of people are kind of asking about, you know, would a helium particle be acceptable? Probably not. Could you use the word stopped? You could, yeah, rather than absorbed, that's fine. And I think a lot of people, a lot of people are asking really good questions. And then after the paper one exam, we're going to switch to paper two, CHOP. So yeah, I reckon now you've only got like a couple of weeks left. So basically, just all focus on paper one. Paper two you can wait. You've got loads of time. You've got half term. Now, from now on, if I was revising, then I would say that, sorry, I'm just going to hide some users. By the way, any bad chat, I just like kind of delete you. Is this more IG or A level? This is more like IGCSE level GCSE. However, it is now 8 o'clock UK time, and we're now going to be going on to some stuff for A level physics. So thank you so much to the GCSE crowd. It's great to see all of you here. Don't forget, I've got hundreds of videos where I can basically teach you the entire GCSE course, including like this last minute revision that's going to get you the kind of top grades. So thank you everybody from GCSE. Now the A-level lot, we're going to kind of continue with a practical that I feel all of you should know about. And this practical for A-level is to do with a way of measuring the Planck constant and also measuring the work function of a metal. Okay, so a lot of you know about Einstein's photoelectric equation, HF equals phi plus Ke max. Okay, we're going to be looking at that. I can see as well that Joe Smith said you finally got to do the resistivity practical today. That's good. At least you've done it before any exams. So yeah, we're going to really sort of focus on like some of the kind of practical side of how you set this up. But again, this practical I'm going to cover, I've got the picture down here, is not something that you have to know. There's nothing in the specification saying that you have to do this particular practical. However, this is the kind of question that could come up in an exam that would kind of really, you know, kind of challenge your current knowledge, but it's based on stuff you currently know. Okay, so this question is the 15th of May. So this is like a year 12 question. I've got more stuff about it in book 3 for my daily workout. And this kind of builds upon the work we did yesterday, looking at this practical to measure Planck's constant, where we had different colour LEDs. And then this is the question we're going to be doing today. And of course, if you have the book, you can see that there are answers in the back. So these are the answers for today's work. And there's also extra stuff on my website. So Mustang, yeah, let's go year 12. Yeah, 8 o'clock, kind of just after 8. We'll kind of tend to do the kind of A-level stuff. I haven't seen the new Veritasium video yet, but I might have a look at it after this. You know, that's, I suppose, how I unwind. Right, so this question is about something called a vacuum photocell. So what we have in here is basically a glass tube that's a vacuum, and at one side we have a metal plate. This could be a metal like zinc or something like that. And what we can do is we can shine light on this. Now, it might be visible light, it might even be ultraviolet, but what we have is this kind of light source or some source of electromagnetic radiation. We shine this radiation onto that plate, and then, because of the photoelectric effect, every time one photon lands on the surface, one photoelectron is emitted, and that can then travel up to this plate over here. Now, if we have the movement of electrons from here to here, we can then detect a current in this circuit. So that's basically how it works. You shine a light on there, electrons leave this plate, they move over to this because it's a vacuum, so the electrons can move through it. And if you have a movement of electrons, we can detect a current. However, what we do is we can adjust the potential difference across this component to actually stop that current. Okay, and so yeah, Joe Smith, yeah, the current is generated by the photoelectrons. So effectively, if an electron goes from here to here, then that's going to cause an electron from here to move around. So the more the higher the intensity of light, the more photons are landing on the surface, the more electrons leave that plate, and they then cause this kind of current around the circuit. But what we can do is we can hold this side here at a potential difference which stops the electrons getting to this side. So effectively, if an electron leaves, I'm going to use a bit of Lego to be in my electron. If there's no potential difference, the electron's just going to leave and it's going to keep moving. If you have a potential difference here which is negative, then the negative electron leaving this plate is going to be repelled by that negative potential difference, and that means there's going to be no current flowing. And although this is an AS question, I reckon you could expect a question like this in a year 13 paper, because in year 13 it includes the whole course. And yes, Jack says, does the orientation of the photo vacuum cell, does the orientation of the vacuum photocell matter? Yes, it does. But effectively, you could just leave that like this and just change the polarity of the connections of that circuit. Okay, and Mustang, yes, this is related to the photoelectric effect, because the reason that electrons are emitted is due to the photoelectric effect, where you've got incident photons landing on a metal surface, and provided we are above the threshold frequency, that means we have enough energy for the electrons to escape the metal. So there's the work function we've got to consider, and then the kinetic energy of the particles. Now, there's lots of information here. If you have the book, obviously you can work through this in your own time, or you can download the questions on my A-level site at alevelphysicsonline.com/live. You can download this question and work through it tonight. So a PD is applied across A and B, with B negative to A. So I'm just going to write that on here. So that's basically negative, and that's positive. So if you have a negative electron which has been emitted, it's going to be repelled from the negative terminal, which is this bit in here. As the PD is gradually increased from 0, at a value Vs, the stopping voltage, the current recorded on the ammeter drops to 0. So basically we can say that the current is 0 when we have a certain potential difference called the stopping potential. Okay, because what we want to do is we want to have a big enough negative charge here to repel the negative electrons. And it says here, this happens when the PD is large enough that the work done in stopping an electron is equal to kV, so Ke max. This is equal to the charge on the electron multiplied by Vs between A and B. So basically what we can say is that the work done in stopping the electron is equal to Ke max, and that can be calculated by looking at EVS. So what this means is that actually there's a link between the stopping potential, which we can just measure using a voltmeter. We know the elementary charge, because that's just a constant of 1.6 times 10 to the minus 19. And if we know these two things, we can actually work out the kinetic energy of the electrons as they leave it. Okay, now that's kind of like the physicsy bit. So I'm going to explain it more. But it says here the frequency of the EM waves is changed and the stopping voltage recorded. So effectively, if you were to shine something like red light at this, we'd have a low energy photon, so we'd only need a low potential difference. If you shine a violet photon, maybe with like a blue laser or like a violet laser, we have more energetic photons, we have more energetic electrons, there's more kinetic energy, and that means we need a bigger stopping potential. If you're like shining ultraviolet light on this, again, the photons have more energy, and for the same work function on that metal, they'd have a higher kinetic energy, so we need a bigger potential difference. If the electron has kinetic energy equal to EVS, what happens to the electron? Yamin, yeah, good question. Basically, if that electron has energy equal to the energy due to the stopping potential, then effectively it's going to get to here and then be repelled. And that means that that's just about no electrons moving. And that happens, this thing up here happens when you have a current of 0. Okay. Right, so the first question is complete the value for the maximum kinetic energy in the table below. So to work out the kinetic energy, all we need to do is multiply this number here by 1.6 times 10 to the minus 19. So for example, you can see here that when we had 1.6 times 10 to the minus 19 times 1.25, that gives an answer of 2 times 10 to the minus 19. So if we just do that for 0.75, we get a value of 2.80. I'm just going to go back, and then we multiply again the elementary charge by this stopping potential, so that's times 2.5. That's 4.00, 3 significant figures. We're just going to continue with this. That's 5.10, and then 6.00. So we now have a link between the frequency and the maximum kinetic energy of those electrons. Okay. Again, I just want to remind you that Einstein's photoelectric equation says that the energy of that photon HF is equal to the work function plus KE max. Now here, that work function is going to be constant because we have the same type of metal. Okay, so we've got a constant work function for whatever metal that is, often zinc or aluminium or something like that. What this then shows is that as we have a higher frequency, as F increases, we should also have a higher kinetic energy of those photoelectrons emitted, because the same amount of energy is being used to kind of liberate them from that metal surface. Okay, is everybody following this so far? By the way, has anybody seen this practical in any textbooks? Has anybody actually done the practical? Has anybody actually seen this demonstrated by their teacher? Or am I teaching everybody, because I know there's a lot of you out there, am I teaching everybody completely new stuff? So have you seen this before? Are you aware of this, or is this the first time you've even heard about it? So Light Arjun says that you have heard about it, but you haven't done it. That makes sense. It's often quite due to that. Yamin says you've seen a question on it before somewhere. Joe Smith, yeah, it's brand new to you, but it seems simple enough. Not really. First time, never done this before. Seen it somewhere on a paper, I think. This is why I'm doing it, because this question here, you don't need to know any of that. The question says, here's an equation. The kinetic energy is equal to EVS. And the first question is just a case of kind of putting numbers into your calculator and multiplying this number by the elementary charge. So the first part doesn't rely on any previous knowledge. It's just, here's the formula. Apply this formula to this part of the table and work out some answers. So this is the kind of thing that could come up. Right. Somebody says, Jack, this is a great question, Jack. I'm really pleased you asked this. What's the relationship between the energy of the photons and the number of electrons released? The two things are not that related. Basically, if you have higher energy, provided it's above the threshold frequency and it allows that electron to be liberated, one photon will only ever liberate one photoelectron. So if you had more energy, you don't liberate more electrons. Instead, the number of photoelectrons emitted, so the size of the current, is related to the intensity of that light. Okay, right, the next one says, use values from the table to plot a graph showing the maximum kinetic energy against frequency. So for this one, what we need to do is just think about a scale. I'm going to go, well, let's see, the frequency along here goes up to 15. So I reckon we've got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so this is our frequency times 10 to the 14 hertz. And the kinetic energy max goes up to 6. So we're going to have 0, 1, 2, 3, 4, 5, 6. Okay, so then we just need to plot the data. This is pretty straightforward. When you've got a frequency of 7, the potential difference is 0.85. So that's kind of about, if that's 1, it's going to be about here somewhere. When this is 8.5, so that's about 8.5, this is going to be equal to 2. I appreciate this isn't as good as the scale that you'll get in the exam, but that's fine. How to find the right scale, Mustang? Yeah, I would say look at the maximum value and just plot the maximum value so you know what it needs to go up to, but using more than half the paper. I reckon, however, in an exam, they won't make you plot the data because it's too time consuming. I reckon instead if there was a question about plotting data, they would give you pre-filled axes and you just have to plot 2 more bits of data and then use that to then work out the line of best fit and so on. So I reckon, Mustang, my prediction is you won't need to find the right scale. That's more of a kind of skill that you've done in your practical work in school. Okay, the next we've got 10 and 2.8. So it's like here we've got 12 and 4. That's a nice one. 13.5 and 5.1. And then we've got 15 and 6. So we've got some data like that. So we have a straight line. And of course with a straight line, we're going to put in a line of best fit. Good question, Holly. I'm going to answer that about in the form y equals mx plus c. So basically, this is the data. Now, I should be doing this in pencil and then maybe going over in pen. But, I'm just going to draw a line that looks like that. Okay, and we can see that this line doesn't go back to the y-axis. So there's no y-intercept in this case. But this plot basically shows how above a certain value of frequency, we then have electrons being emitted. Now what that really means, and I think this is kind of the key, most important, exciting, interesting thing about this, is that there's basically going to be some kind of certain frequency. Below that frequency, nothing is emitted. No photoelectrons are emitted. Above this point, we then have photons emitted, and then the higher the energy, due to the frequency of that electromagnetic radiation, the higher the frequency, we then have this linear kind of increase, or this directly proportional increase in the kinetic energy max, the maximum possible kinetic energy of these photoelectrons. So calculate the gradient of your graph, and this should be equal to the Planck constant. So the gradient, m, is just going to be equal to our change in y by our change in x values. Of course, you need to then kind of draw in your triangle like that. Okay, so this is the triangle that we're drawing just now. The change in y value, I'm just going to add a few more numbers. So you've got 7, 8. That's going to be equal to, I reckon, about 7.2 minus 0 divided by, that's 15, so that's going to be 17 minus about 5.8 roughly. So 7.2 divided by 17 minus 5.8 is equal to 0.642. Okay, now that is not the Planck constant, but what we've got here is actually the change in y value is times 10 to the minus 19, and the change in x value is times 10 to the 14. So we should really have this value here. We multiply by 10 to the minus 19, and we divide by 10 to the 14. Okay, now that then is going to be equal to 0.642 times 10 to the minus 33, which is equal to 6.42 times 10 to the minus 34. Is that right? Yeah, I think so. Okay, this is the answer. And effectively what we're saying here is that gradient is equal to the Planck constant. Okay, great stuff in the chat, by the way. Loads of people here talking about their exams, which are like just about a week away. If you've got AS exams, I know it's really, really close. And the same for your GCSEs. I know that GCSEs, I think, is it next Thursday they start with RE and then biology on the Friday. So I know that all of you, it's like, it's going to kind of happen. And then I know that all of you are going to be absolutely fine. So the Planck constant here is equal to the gradient of that line. So here, the gradient is equal to h. Now the reason for that is that we know from Einstein's equation that hf equals phi plus ke max. Okay, now what we've got here on the y-axis, we've got ke. On the x-axis, we've got f. So if we write this in the form of y equals y equals mx plus c, we can say that ke max is equal to, what is it? It's going to be equal to HF minus phi. Okay, so we've got on the y-axis the kinetic energy. H is going to be equal to the gradient. The frequency is x, and that means the y-intercept is going to be equal to minus phi. So what we've done here is the gradient of this line is equal to the Planck constant. And I think that's what Holly said. Yeah, so basically, and I think that's a really kind of good leap there. We've got a line which is a straight line, and therefore there's going to be something represented in a physics exam by the gradient and something represented by the intercept. We can also then use the intercept on the frequency axis to calculate the work function. Now effectively, below this value of frequency here, no photoelectrons are emitted, so this is what we call F0. That is the kind of that kind of the threshold frequency below which no photoelectrons are emitted. And if we look at this equation over here, we can say that HF0 is equal to phi when the kinetic energy is 0. So when you've got the threshold frequency times the Planck constant, that's equal to the work function. And so, yeah, the x-intercept is the threshold frequency and the y-intercept is the work function. Mads, yeah, completely correct. Now, that means the work function is going to be equal to the threshold frequency, which in this case is 5.8 times 10 to the 14 hertz, multiplied by the Planck constant, or indeed you could just use a gradient here. We know, of course, though, that the actual value for h should be 6.63 times 10 to the minus 34. And if you do that, we get a value for this equal to about 3.8454, so 3.8 times 10 to the minus 19 joules. But we need to know this answer in electron volts. And to convert from joules to electron volts, we just divide by 1.6 times 10 to the minus 19. And that's going to be equal to about 2.4 electron volts, which is kind of the number we expect. Right, Mustang, yeah, really appreciate the love there. Hopefully, I saved you from your mocks. I'm sure you put in a huge amount of work to get there. Okay, so this way here is another way that you can use your existing knowledge, maybe for some of you in an unfamiliar context, to work out the Planck constant. So you can either work out the Planck constant when you're using LEDs that just about turn on. When the current flows, you've got this threshold voltage or whatever. This way is using a vacuum photocell to work out the stopping potential, and then that stopping potential allows you to plot a graph like this, where the gradient is the Planck constant and the x-intercept is the threshold frequency, or indeed the y-intercept down here would be the work function of that material. So that is basically the end of the live stream tonight. Does anybody have any questions? It's great to see so many new people in the chat. Holly, Jack, Mustang, MAE, Mads, Questionable, Linkslet. Yeah, so many new people. Joe Smith says, does one electron volt come from an electron going from a 0 volt plate to a 1 volt plate? Yeah. So the definition of an electron volt is that 1 electron volt is the energy gained by 1 electron accelerated through a potential difference of 1 volt. So it's basically 1 electron times 1 volt as a potential difference. And this is coming from the fact that the energy gained is equal to be QV, where the charge is just the elementary charge and the V is just that 1 volt. Okay, tips for going from an 8 to a 9 in physics. I reckon it's just a case of, and this is a good thing, I think a lot of people actually down here in the chat I think a lot of people here will have done really well at GCSE. If you're in the chat at the moment, you're either a GCSE student, kind of working out how to get to the highest levels, because you're thinking about A-level physics. If you're doing A-level, I know lots of you will have got really good things. So, yeah. Tips to go from an 8 to a 9, I think it's just a case of just as many past papers. I mean, I'm going to say that I've got like these practice papers that you should buy, and they will really stretch you. Those are the most difficult questions. And if you're doing difficult questions, if you're doing questions from Isaac Physics, I think those ones are really good for the numerical working, and also just learning the basics and not forgetting that there will be lots of easy questions that get you easy marks, but don't think everything's going to be complicated. There are so many easy things about definitions, about suggestions, about labelling equipment, that don't forget the basics if you want to get those high marks. Rohan says, does 500 volts mean 500 electron volts? Yeah, so basically if 1 electron volt is 1 electron through 1 volt, then if you accelerated 1 electron by a potential difference of 500 volts, it would gain 500 electron volts of energy. Any tips on learning electricity? It's just a case of questions. If you just want to find electricity questions, there are some good ones that you can find over on Physics and Maths Tutor, where they've got AQA questions about electricity, but just doing as many questions as possible. Just sit, do as many electrical questions on either physics. You can choose the questions, or you can do the game board from the book, and it's just question after question after question. Right. Yeah. Definitely lots of people here. People going to do A-level physics for A-level. That's awesome. How should you answer 6 markers, Madam Pinky? I reckon a 6 marker, break it down to 3 2-mark questions. So when you see that 6 marker in the exam and you think, oh, I can't do this, I don't know anything, I guess within the question there might be sub-questions within it. So maybe circle them as like 3 sub-questions and think, okay, can I get 2 marks for this bit? Can I get 2 marks for that and 2 marks for that? So think of it as 3 2-mark questions. Okay. What exam board should you practice if you've done all your OCR papers? I reckon, Jack, you should do AQA or Edexcel papers, but just have the spec with you. So if you see a question and you think, I don't know anything about this, then you know that actually that's not that you don't know the physics, it's just that it's a topic that doesn't come up for OCR. But I would say for AS Physics, Year 12, it's pretty much all the same, but just have the spec and know what is coming up in your exam, and that means you can do other boards past papers. Right, are paper 2 A-level physics questions more calculation based or theory based? I would say that compared to GCSE it's a lot more calculations, but I think paper 1 and paper 2 are fairly consistent in terms of the number of calculations. I think they both get the same amount of marks for those kind of questions, so I think that it's not like paper 1 is theory and paper 2 is calculations. Both exam papers, and I think paper 3 as well, are pretty much all equally spaced out with these calculations. So you need calculations for everything. I reckon that is the end of it. Can I just ask all of you to go and speak to your parents really nicely, and go and buy some stuff. I've got a link at the top of the chat. What I'll do is I will... oh, I've done something stupid to my chat. I will basically ask all of you, go and have a look at my physics online shop. There might be things in there that you find useful. Also, make sure that you do have a look at GCSE or A-level physics online. There are so many things there that can help you over the next couple of weeks to go from here, which is like a really high point, just that little bit higher, to kind of give you a few more marks, and also actually feel a bit more confident. So you know that 24 hours a day you can just go to my website and find a video where I explain that physics to you. Okay. What's the difference, Sam? This is a really good question. What's the difference between threshold frequency and the work function, except that one is energy, one is frequency? I would say the difference is that the threshold frequency is the frequency of the radiation needed to emit an electron from the surface of that metal. Okay, so this is about the energy needed by the electron, and this is about the energy of the photon that interacts with that one electron. When are the live streams for future reference? Harry, excellent question. What I'll do is, if you want to find out when my next live streams are, I've basically put them all up on my website. You can see exactly the topics that we're doing for the next few weeks. And what I'll do is just post a link to it. So you can just go to alevelphysicsonline.com/live. So I'm just trying to find my chat, and basically it's this page over here. So you can see, MAE, thank you so much, by the way. Yeah, it's a live button on the top right, the red button. I should probably do like a bigger red button really at some point, so it's like quite clear exactly which page to go to. The other thing that all of you can do, and I'd love you to do this, is I've got my other website, my main one, which is physicsonline.com. Again, I'll put a link up to that in the chat now. But if you sign up to my newsletter, then I'll give you more information every single week about the live streams coming up. Okay. Also, Mads, 1 o'clock in the morning, get to sleep. Sleep is important. Where is it is this, yeah, because I know there's people all over the world. I know a lot of people are UK based, but if you're doing international A-levels, it's great to connect with so many people. I know there's somebody from Dubai yesterday, we've got people from Pakistan today. It's great to have so many people around the world who are actually doing identical physics to all the stuff that's being done in the UK and all over the world, actually. You are not alone. If you're struggling with bits of physics, it doesn't matter where in the world you are, the physics is identical. So that's awesome to have so many people all over the place. Okay, so it's 10:30 there, Mustang. No way, that's awesome. Sri Lanka, yeah, I know a lot of people in Sri Lanka use my stuff, so it's great to have all of you on board. So thank you, everybody, and good night. I will be back again on Monday night. I don't know what the date is, but on Monday night I'll be back after the kind of bank holiday weekend, and I'll be doing some more lives then. All right, thank you, everybody, and goodbye.